Hello students and welcome to today's Friday Happy Math Hour. Today I'm going to cover exam 2 review for the 0324 and 3024 course. Okay, so these are the topics that I'm going to cover. They go all the way from 4.1 to 5.4, which are going to be graphing exponential functions, application of exponential functions, 4.2, graphing logarithmic functions, 4.3, writing exponential equations into logarithmic equations and vice versa, which is 4.3, expanding and condensing logarithms, is also from 4.3, and solving exponential and logarithmic equations, which is section 4.4. And then chapter 5 is the one that I presented last week, which is, finance mathematics. Simple interest is 5.1. Compound interest is 5.2, and future value of ordinary annuities 5.3, and the present value of ordinary annuities 5.4. So let's start with topic number 1, which is graphing exponential functions. So number 1 is graph f of x equals to 2x. Okay. These are the points that are self-students that are most frequently used. You're going to use -2, -1, 0, 1, 2, and 3 for x. Okay, so let's draw ourselves a little table. That's x, and that's f of x, which is f of x is also equal to y. Okay, so let's do our table. -2. So when x equals -2, and you see here on the right on the screen, I'm gonna evaluate f of -2, which means I'm gonna plug in -2 for the x, which is the exponent. And then by applying some of the exponential rules for the negative exponent, right? So this becomes a 1 over 2 squared, which is going to be 1/4. So when x is -2, y is 1/4. Now we're going to do it for f of -1, when x equals -1. So then we're going to plug in -1 where the x is on the original function, which that equals to 1 over 2 to the first power, which is equal to 1/2. If you have a calculator, you can actually put it just the way it is, like this, 2 to the -1 power. It's going to give you something like 0.5, and then you know it's going to be 1/2. Okay. So then when x is 0, right, we repeat the process. So y equals 1. When x is 1, again repeating the process, we're going to plug in 1 for the x. So y equals 2. And when x equals 2, we evaluate at f of 2, which is going to give us 4. So y equals 4. And finally, when x equals 3, we evaluate f of 3, will give us 8. So then we draw our graph. Okay? So for example, the graph of an exponential function, this will be like the parent function. It will always go something like this, guys. And if you notice, when x is -2, right, this is -2, y is 1/4, which means that between 0 and 1 here for the y value, I'm going to cut it into 4 equal parts. So 1/4 will be about right there. Then when x is -1, right, this is -1 for x, it means that I'm going to cut this unit from 0 to 1 into 2 places, right, in half, so that's half. And when x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. And when x is 3, y will be 8. That's why most of the times these are the values to use for x. Because if we were to plug in say 4 for x, then it would have been 2 to the 4th power, which would be 16, and you'll be way up here. So it's going to be out of the range. So again, that's why this is the values that we frequently use. Okay. Now what happens if we graph f of x equals to 2x minus 1? We can do it by plotting the table, right? But as we should know from the graph transformations, this is like the parent graph. So you have 2x minus 1. This means there's going to be a horizontal shift. So everything is going to shift 1 unit to the right. Okay, but let's say you didn't know that. So then let's actually do the work. Okay. So again, we use the same values. When x is -2, right? I'm going to go here to my function, which is f of x equals to 2x minus 1. And I'm going to plug in -2 for the x. So this will give me 2 to the -3rd power. This will be 1 over 2 cubed, which will give us 1/8. So when x is -2, y is going to be 1/8. And then we just keep repeating the process. Okay, we're going to plug in -1 there for the x. So it's going to give us x to a -2. It's going to give us 1/4. So when x is 0, we plug in 0 for the x. So 0 minus 1 is going to give us 1/2. When x is 1, we find f of 1. Again, we plug in 1 for the x on the original function. So we're going to get 2 to the 0, which is equal to 1. And it's 2 again, repeating the process. It's going to give us 2 to the 1st power, which is equal to 2. So y is 2. And finally, f of 3 is going to give us 2 to the 2nd power, which will give us 4. And let's do one more. When it's 4, it's going to give f of 4. We're going to plug in 4 for the x, which will be 2 to the 4 minus 1, which will give us 2 cubed, which will give us 8. Now there's my graph. If you notice, if you notice here, when x is -2, right? X is -2, it means that I'm going to cut this unit here at 1 into 8 equal parts. So that's why when it's -2, it's real close to the y-axis. Then when it's -1, it's going to be 1/4. When it's 0, it's 1/2. When it's 1, it's going to give us 1. When it's 2, it's going to give us 2. It's going to give us 2. When it's 3, 1, 2, 3 is going to give us 4. When it's 4, 1, 2, 3, 4 is going to give us 8. So it's going to be way up here. That's how you draw this graph. If you notice here, when it was 0, right, it was 1. So if it shifts 1 unit to the right, so then at 1, it's going to be 1. You see here it is. When it was 1, right, it's going to be 2. Now, if it shifts 1 unit to the right, that means that we're going to add 1 here to the x value. So when it's 2, it's going to give us 2. That's what I mean by the horizontal shift, is that this graph comes out of this one here from f of x equals to 2x, but this graph shifts 1 unit to the right. So everything from here, guys, gets shifted 1 unit to the right. That's how we came up with this graph here at the bottom, number 2. But if you didn't know that, you can actually graph it like we just did. Okay? Now, let's do g of x equals 2 to the negative x. Remember the rules for the exponential rules for negative exponents, right? It becomes 1 over, you do the reciprocal, or else you put 1 over it, and it becomes positive. Eventually, this is similar to 1/2 to the x power. Remember when I said last week, if you have, this is the same thing as 2 over 1, correct? You do the reciprocal, and this becomes positive. So this was like 2 over 1 to the negative x power. You do the reciprocal, and it becomes positive. Okay. And again, so this graph, it's already graphed here, guys. So all we do is, when x is -3, right? So we're going to put in -3 there. So it's going to give us, right? We do the reciprocal. So it's going to give us 8. And then when you see give us 8, right? And then when it's -2, I'm going to repeat the process for all these values here. Right? If you repeat the process, we get all these y values here. And you have to do it, just plug into the calculator if you want, in a calculator, or do it by hand and repeat the process that I just did. So for example, if it's -2, right? If it's -2, I'm going to plug in -2 here. So since it's negative, we do the reciprocal, which will be 2 over 1 to the 2nd power, is going to give us 4. That's where the 4 came from. That's how all these values come, is by actually evaluating the function at these x values. Okay, so this will be my graph. Okay. Okay, now, Maciel, if you have any questions, Mr. Vasquez, please raise your hand up, and that way you can stop me and I can explain to you. Okay? Okay, now this is number 4. It says, the assets in billions of dollars of Prudential Financial Incorporated can be approximated by the function AX equals to 315 e to the 0.056x, where x equals 7 corresponds to the year 2007. Find the assets for the following years. So what we do for this problem here, all we do is that we're going to plug in, for example, this is my solution. So since x equals 7 corresponds to the year 2007, so then x equals 0 corresponds to the year 2000. So for A part, I'm going to find, I'm going to evaluate at A of 0. Okay? So A of 0, we're going to plug in 0 for the x right here, right, on the exponent. So it's going to give us 315 e to the 0. Anything to a 0 power will give us 1. So 315 times 1 will give us 315. So this is the answer for A. But right, since it was in billions, it's going to be $315 billion. This is good to know, guys. 315 is the initial value because time is 0. I think we're going to be using it on the next problem. Okay, now for B, right? We're going to evaluate A of 12 because here in the solution, right, if x equals 7 corresponds to the year 2007, then x equals 0 corresponds to the year 2000. So therefore, x equals 12 will correspond to the year 2012. So we're going to evaluate A of 12, which means I'm going to plug in 12 for the exponent. For the x's on the exponent. Again, this is a common mistake that students make. It depends on your calculator. If the calculator gives you like a little box to plug in the exponent, well then there's no issue with that. But if when you plug in the e value from your calculator, if it gives you parentheses, then you have to put 0.056 times 12 and then close up parentheses, because if not, you're going to get the wrong result. So please be careful with this. It depends on the calculator that you're using. So again, this will give us 616.8171575. So that becomes like $606.8 billion. Okay. Now this is number 5. I remember when I was teaching this course here back in 2020, the spring. That was when COVID had just started. So I use that example of COVID, the virus, how to figure out how we can use the situation of COVID and use an exponential function to get the exponential function. So this example is used, right? We're going to use it to find a function that will that we can find at any time how many cases or how many people will be infected. Okay, so here's number 5. It states a deadly virus has infected the world. At the end of January, there were 2 cases, and by the end of April, the cases had grown to 128. I believe I use this example. I'm here in the United States because I remember towards the end of January, there were 2 cases, I believe, in Washington. And then by the end of April, there were 128 cases, I believe, in the United States or something like that. So let's use a scenario to find the model and then to see how many people will be infected by the end of the year if there was no intervention. So here's my solution. Okay, we need to find y naught and b, right, for the formula here. So y naught is the amount present at time 0. So for example, since t equals 0 corresponds to the end of January, right, because when the cases were reported, there were 2 cases, so it's going to be 0, 2. Y naught will be 2, or the point will be 0, 2. So, right, so t equals 1 will correspond to the end of February, right? Because here at the end of January was when t equals 0. So t equals 1 corresponds to the end of February, t equals 2 corresponds to the end of March, and t equals 3 corresponds to the end of April. Because here it said here in the word problem that there were 2 cases. There were 2 cases by the end of April. There were 2 cases, and by the end of April, the cases had grown to 128. Right? By the end of April, there were 128 cases. So that's why we're going to find there were 128 cases by the end of April. So this is going to give us 3. To find B, right, we're going to use 3 was 128. So f of 3 is 128, and we already found the y0, which is 2, which was the initial cases was 2. Okay, so we're going to plug in 128 here for the f of t, and then my y0 is 2, and then b, right, and this was a time, which is 3 months later, so that'll be our time will be 3. We plug it in for the t. Then we divide both sides by 2. This will give us 64 equals b cubed. Then we raise b cubed to the 1/3 power, both sides. So b will be 4 because 64 to the 1/3 power will give us 4. So b is equal to 4. So I already found my b and I already found my a. Right, so I mean my y0. My y0 is 2 and my b is 4. So let's plug into the formula. So this becomes my exponential formula. There's my y0 is 2 and my b is 4. So this is the answer for A part. Okay. Now, for B part, right, we have to go from January all the way to December. Right, because if we continue here, guys, t equals 4 corresponds to the end of May, t equals 5 to the end of June, and so forth. We're going to say that t equals 11 corresponds to December, to the end of December, to the end of the year. That's why we're going to find f of 11. So this is how many cases there will be if there was no intervention. And again, how do we find 11? Because if t equals 0 corresponds to the end of January, right? There's 12 months, but January is already accounted for because that's when it started. So from January to December, right, is going to be 11 months. That's why by the end of December is going to be 11 months. So we evaluate f of 11. So this is how we use these type of problems for exponential functions. Okay, now we're going to be solving exponential equations. So here's like the definition of like a formula. It says let a be a positive real number with a cannot be equal to 1. If a to the u power equals a to the b power, then u must equal to b. Okay. So example, we have to have the same base. That's what the rule says. We have to have the same base for us to apply the rule. In this case, example, right, we have the same base, which is 3 and 3. So then x will be equal to 5. Okay. Now number 6, solve for x. If we notice 125 and 5 are not the same base. So we have to make them the same base. We should know from previous workshops, or if you know perfect roots, perfect squares or perfect cubes, right? We know that 5 cubed will be what will give us 125. So I'm going to replace 125 with 5 to the 3rd power. Right, and then we just bring down the x equals to 5 to the 5th power. Then here we apply the exponential power rule, which means we multiply the power. So 5 to the 3x equals to 5 to the 5th power. Now we got the same base, so we can apply the rule. So 3x equals to 5. So divide both sides by 3. So x equals to 5 over 3. And you can always check your work. Okay, you can always check your solution. Right, we said that x equals to 5/3, so we're going to plug in for the x. Then guys, if you plug this in the calculator, 125 to the 5/3 power is going to give us 3,125, for both of them. So we know this is the correct answer. And again, be real careful when you plug in a fraction as an exponent into the calculator. Most of the times, it's wise to put it with parentheses. This way, you will eliminate some of the mistakes. Okay. Solving exponential equations continue. So here's another one, okay, but this is a little bit more challenging. So again, we have to make them the same base, right, because these are not the same base. So then we can say 4 squared equals 16, right? And 16 does that equal to 32. And 4 to the 3rd power will give me 64. and 64 does not equal to 32. If you notice, 16 is less than 32, and 64 is more than 32, which means I have to find the same base between both numbers. So 4 is not a common base. So then 4 is equal to 2 squared, and 32 equals to 2 to the 5th power. You see, I found my common base, which is 2. So now I'm going to substitute 2 squared for the 4, right? Which was over here on the right. And then we bring down the x minus 1. Then I'm going to substitute 2 to the 5th power for 32. Then here we apply the exponential rule, the exponential power rule, which means when you have a power to a power, you multiply the powers. So this I'm going to multiply 2 times x minus 1 equals 2 to the 5th power. Right, now we have the same base. Now we can apply the rule. When you have the same base, the exponents must equal to each other. Now here I'm going to distribute. So give us 2x minus 2 equals 5. Then we solve for x by adding 2 to both sides. So 5 plus 2 will give us 7. So 2x equals 7. Now we divide both sides by 2. Will give us 7 over 2. So this is my solution. And again, we can always check our work. Just plug in 7 over 2 for the x. Right, 7 over 2 minus 1 will give us 5 over 2. Now, if we plug that in the calculator, 4 to the power of 5 over 2 is going to give us 32. So 32 equals 32. So I know this is the right solution. Okay. Now, this is writing exponential equations into logarithmic equations and vice versa. So there's a rule that you got to know. Okay, but before we do that, here's a definition of logarithms to base A. Here's the rule that I was talking about. If you have y equals to log of base a to the x, means a to the y equals x. Some books use a for the base, and in others, they use b for the base. I like to use the b instead, but I just followed what was in the book, which was a. So write the logarithmic equation into an exponential. There's my logarithmic equation, so it's going to be in this form here, right? So I have to find what the y is, what the a is, and what the x is. Right, so I have to find a, x, and y. So here, guys, we know that a will be my 9, right? A is 9. We know that x is 81. And we know that y is equal to 2. So now we have 9 squared equals 81, right? Because my a is 9, right? From here. My y is 2. Y is 2, and x equals to 81. That's how we go from logarithmic into exponential equation. Now we're going the other way. We're going from right-ish exponential equation into a logarithmic equation. So again, right, so now it's going to be in this form, so I know my a, we have to go from exponential to logarithmic, so I know my a will be 5, my y is 3, and my x is 125. So it's going to be, right, my y is 3, so that's why it's 3, because y is 3. There's my y. My a is 5, right, from here. And my x is 125. So this is my solution, or else you can put it the other way. I believe in back of the book, the solutions is going to be in this form, but it doesn't matter if it's log of base 5 of 125 equals 3, or 3 equals to log of 5 of 125. It's the same thing. Now, logarithmic function graphs. So this is crucial here, guys. In order to graph without a calculator, you must convert the logarithmic equation to an exponential equation. So let's say, again, we have to use the same rule as before. So let's say they give you y equals log of base 2 of x. That's going to be 2 to the y equals x. So then just do our table. But now, instead of plugging in the values for x, we're going to plug it in for y, because it'll be much, much easier to plug it in for y. Right, so here we go. So if we plug in negative 2 for y, it's going to give us, right, it's going to give us x equals to 1/4. And if we keep repeating the process, this is what we get on the right-hand side. We plug in -1 for y, it's going to give us 1/2, and we plug in 1 for y, it's going to give us 2, and we plug in 0 for y, it's going to give us 1. We plug in 1 for y, it's going to give us 2, the x is 2, and we plug in 2 for y, it's going to give us 4 for the x, and then we plug in 3 for the y, it's going to give us 8, because 2 to the third power will give us 8 for the x. So then to graph it, right, so we repeat the process. You see what I'm doing there? That's what I just mentioned, right? If we keep repeating the process, this is how we get. So there's my graph. This is the exponential in blue, and this is a logarithmic equation in red. Okay? And these two are called inverse of each other. Okay? But I believe in 1324, I believe we don't cover that. Okay? So let's just move on. Now here comes the expand or condense logarithmic expressions. So these are the properties that you have to be aware of. Right? They can be the logs or they can be the ln. This is natural log and this is the regular log. This is called the product rule. If you notice, the product means this is called single log. This is called expanded log. There's another word. Single log can also be called condensed and expanded, or single log and expanded. If you notice, right, if you have the product here multiplying x times y, you can separate the logs. It's going to be addition in between. If you divide them, it's going to be subtraction in between. And notice here, right, if you have log a to the x to the r power, the r comes to the front. So in other words, when it's in a single log, you can have no numbers in the front. They become your exponent. And when you expand them, right, there should be no exponents. The exponent will go to the front. That's when we work these rules here. And also the same properties work for the ln. So let's here write each expression as sum and or difference of logarithms with the variables to the first degree. So these are some students, right? So which properties are present? If you notice, here we have log of 5x to the fourth power, y cubed, right? So this is in a single log. So we have to write it in expanded form. So we know that the product rule is there, right? Because this is a product, and also the power rule because we have the exponent. So then we need to add three separate log terms, right? Because we have here the 5, we have the x, and we have the y, right? So these are like 5. This is a coefficient, this is a variable and a variable. So we're going to have them in three separate logs. There's 1, there's 2, and there's 3. Now, right, if you notice, if it's expanded, there's no exponents here. So the exponent must come to the front. You see, exponent goes to the front. So the 4 goes to the front, and the 3 goes to the front. So this is your solution. Okay, let me go back real quick. Right, so again, this will be a solution. I tell my students, if you have here, like, maybe I use the wrong by separate log terms, right? So we separate it in three different terms. But the 5, right, will be like one term with a log, and the x to the 4th will be another one, and y cubed will be another one. So if we have here also like a w, then we will separate them in four terms. Okay. Now we're going to go the other way. Again, we have the rules there. So now we write each expression as sum or difference without variables to the first degree. Now, right now it's still condensed, right? So we're going to expand them. Which properties are present? So we know we have the product rule, right? Because we're multiplying. We have the division rule or the quotient rule, and we have the power rule. So here we're going to apply all the rules. Okay. So again, right? So first we're going to apply the product rule. Right, and then the quotient means subtract. This is applying this rule here on the second rule. Then we're going to apply the product rule here. So if it's product here, we're going to be adding them. Right? Now, right now, if we notice, if it's expanded, there's no exponent, so the exponents must go to the front. Here's where we apply, execute the power property. Exponents goes to the front. So then this will be my result. You see the 2 goes to the front. Okay, now, there's a way that I tell my students how to do this one. Okay, I tell them, how many variables are there? There's 1, 2, 3, right? There's 1, 2, and 3. So there's going to be three terms, three log terms, 1, 2, and 3. If it's if you multiply in here, right? If you multiply in here, it's going to be addition. So these two are addition. If it's in a fraction, the denominator will be the minus the denominator. You see, this is my denominator w, like over here on the x divided by y. So that will be the minus the denominator when it turns up log. So again, this is step by step. And the observation was, if you have 3 variables, so you can have 3 different logs. If you have multiplication, it's going to be addition. You have division, it's going to be subtraction. And if you have exponents, the exponents will go to the front, like they did here. So this is my solution here. Again, now we are going the other way. Right, so now we have to put them as a single log. So if we notice, here we have 2 properties. We have the quotient, right? The power and the quotient, right? This becomes the power, right? Because this goes to the front. So then, if it's minus, right, it's going to be division. We have to write it as a single log. The exponent goes to the front. And then we have to write it as a single log. Right, so this is my numerator, right? My numerator is here. And the denominator is the one that subtracts from the numerator here, guys. This is my denominator and my numerator. You see from the rule here. My numerator is the first one. My denominator will be your second one. But they're all in terms of log to whatever the base is. But in this case, it was the ln, so it's the one on the right. Okay, so that's your solution. Let's do another one. I mean, if here, guys, we're trying to solve. Okay, I guess when you solve, the first step was to see if you could find the same base, right? But there's another way to do it without using the same base. Here, we're going to take the ln on both sides. Right? We have to bring down the x, so we're going to take the ln on both sides. With the ln, guys, right? So then we can apply this rule here. The exponent comes to the front, so the x comes to the front. Exponent goes to the front. So we have x, ln of 6 is equals to ln of 72. Then we divide both sides by the ln of 72 of 6. I'm sorry. I'm going to put that in the calculator. So we should get something like 2.386852807. And then it depends on your My Math Lab or your instructor to how many places should you round it off. In this case, I believe we said 4, which means if it's 4, we're going to go to the 5th one. There's 1, 2, 3, 4, 5. If this number here on this log here is 5 or more, then you add 1 to the one to the left. That's why it was 5 or more, so we added 1 to the 8, which was 9. So this is my approximate solution. Okay, and again, it's very important, guys, that the ln of 6 is a number. The ln of a number is an actual number. You cannot separate these two. That's why we divided by the ln of 6, because it's a number. Please don't forget that. Okay. Now here we're going to use another rule. If you have log of u, then u, v, and a be positive real numbers with a not equal to 1. So if log of a, if log of base k of u equals to log of base a of v, then u will equal v. So number 15, in order to apply this rule here, we have to have a single log on both sides, right? So we're okay on the left, but on the right, we have to convert it to a single log. If you notice, going back to the rules from before, when you're subtracting, right? When you're subtracting, you're going to use a quotient rule. What you be is going to be the log of x plus 3 over x minus 1. And when there's no base, it means it's base 10. Okay, so this is like base 10. When there's no base again, it's base 10 on both sides. Now we can apply the rule. Okay. So then x equals to x plus 3 over x minus 1. Then here we can cross multiply, which will give us x times x minus 1 equals to x plus 3. Then here we're going to distribute, gives us x squared minus x equals to x plus 3. Now we have to let it equal to 0. Why? Because we have a quadratic equation. So we're going to set the equation equal to 0 by sending the terms on the right side onto the left by doing the opposite. So it'll give us negative x minus 3, but we'll do it to both sides. So the right side is going to give us 0. On the left side is going to give us x squared. Negative x minus x will give us negative 2x, and we keep the negative 3. Now here we have to factor. This is a factorized form of the trinomial x squared minus 2x minus 3. Okay, and this is crucial to know how to factor, guys. You have to know how to factor. Anyway, then we apply this is called set by numbers equal to 0, which is the same thing as applying I believe it's called the zero property rule, which means we have to let x minus 3 equals 0 and x plus 1 equals 0. So then, right, we solve for x on both sides. So x equals 3 and x equals to negative 1. We can check both sides, right? But one thing that I want to tell you that the logs cannot be negative. You see, if we plug in negative 1 there, it's going to be undefined, so the logs cannot be negative. See, not defined. So that means negative 1 is not a solution. Then we plug in 3. We're going to plug in 3 there for the x, for this x, and also for this x here. Then we simplify, right? This will give us 3 plus 3 is 6. Now here, guys, here, right, we're going to apply the quotient rule, right? We're going to condense it. Or you can use a calculator, and you're going to get that right there on both. So that's true. Or we can apply the quotient rule from the quotient property. This becomes, right, a single log will be 6 divided by 2, which will give us 3. You see, guys, they're the same. This is how to use it with a calculator. This is how to use it without a calculator. So it's up to you how you want to check it. Okay, so that's a solution. Now here's another one. If it says if a and u are positive real numbers where they cannot equal to 1, then if you have a to the exponent of log of base a to the u, it will equal u. So in other words, if the base, right, this will be my base, and the base of the log are the same, that's equal to 1. So for example, in this case, to apply the rule, right, we don't want the log of base 4 there. So we're going to put a 4, right? We need to cancel the log of base 4. So we're going to put a big 4 on both sides. You see, let the expression on both sides, let these expressions be your exponent. So we're going to put a big 4 on both sides. You see, now by applying this rule here, by applying the rule, 4 to the power of log of base 4 of x plus 6 will give us 5x plus 6 equals to 4 squared, which will give us 5x plus 6 equals to 16. Then we solve for x, subtract 6 from both sides, so 5x equals 10. We divide both sides by 2, and it should by 5, and it should give us 2 as the answer. My bad, I was thinking about the answer already. So the answer is 2. And again, you can always check your solution. Right, I'm going to plug in 2 for the x, which will give us 10 plus 6 will give us 16. Log of 4 to the 16th power is going to give us 2. So 2 equals 2. And here, guys, you can apply the change of base if you want to. Or this is how you read it. It reads 4 to 4th power will give me 16. Right? So 4 to 4th power will give me 16. So 4 to the 2nd power will give me 16. That's how you read it. You can apply, put this in the calculator by using the change of base property. Or you can use without a calculator how I just did it. So it's up to you how you want to get the answer. But log of base 4 of 16 equals to 2. That means that 2 is the correct answer. Now comes material from chapter 5. Okay. Since here, this is number 17. Gabriel invested his summer earnings of $3,000 in a savings account for college. This account pays 1.5% simple interest. What will be the value of this account after 2 years? And how much interest did he earn? So this is a simple, right, simple interest formula here, right? Because it says simple interest, where is it at? Here, 1.5 simple interest. So this is a formula for 5.1, which is a simple interest formula. Since we're looking for the future value, right? The value after 2 years, it means we're going to use this formula here. So we have to extract the information from this word column. So what will be the value of this account in 2 years? So we're looking for FIV, right, which is the future value. So then the 3,000 is how much Gabriel invested right now, which is 3,000. My R will be the number with a percent symbol, which will be 1.5%. You convert that into a decimal, it's going to give us 0.015. And the time in years will be 2. So all we do is plug into the formula, right? And we use a calculator, and that's our result. So then, right, so this is my answer for the future value. This is how much money will be in the account. Now for the second part, how much interest did he earn? So for the interest is a future value minus a present value. So if you started out with 3,000, right, and then you end up with 3,090, that means that 90 will be the interest. Okay, we can plug it into the formula. We should get 90. That's how much money Gabriel earned from the account. So the value of the account after 2 years will be 3,090, and the interest earned will be $90. So these are my solutions. Okay. Now this is something from 5.2, compound interest. That's my formula, but I prefer to use this formula because it's easier to put in the calculator. If you notice, my Rm is represented by I, and my MT is represented by N. So this is what everything is, okay? And I believe I went over this material last week on the previous workshop. But anyway, my future value is a future or the maturity value. The PV is the principal or the present value. My R is the interest rate per period converted to a decimal. My M is the number of compounding periods per year. T is the number of years, and the I is R divided by M. And the N is M times T, which is the total number of compounded periods. And here's what the values, here's what the keywords for M is. If it's yearly or annually, M is equal to 1. Bi-yearly or semi-annually, M is equal to 2. Quarterly, M is equal to 4. Monthly, M is 12. Weekly is 52. And daily, it can be 360 or 365. It's going to be 365, okay? If you don't see nothing in the book to use 360, you all use 365. But there's some books that they want you to use 360 for daily. And if it's continuous, it's a different formula. Okay? So this is crucial to know. These, the compounded, you're going to use them for 5.2, 5.3, and 5.4. Okay, now compound interest can be used to invest a certain amount of money without depositing additional money. Here's an example. 18. You deposit $9,000 in an account at your bank that pays 2.5% interest semi-annually. How much money will be in your account after 10 years? And how much interest did you earn? So let's put the formula down. Right, which is this one's easier. Now this is going to be 7 variables. Okay, 7 variables. You see 1, 2, 3, 4, 5, 6, 7. For sections 5.2, 5.3, and 5.4, there will always be 7 variables that you need to extract from the word problem. So first of all here, what are we looking for? We're looking for how much money will be in your account after 10 years. So we're looking for the future value. So then the 9,000 must be the present value because that's the money that you deposited right now. So that's my 9,000. My interest rate will be the 2.5%. Converted to a decimal will give us 0.025. My M is the number of compounded, right, which is semi-annually, which is 2. My T in years will be 10. Now the I, right, we already have enough info to get my I, which is the R divided by N. 0.025 divided by 2. which will give us 0.0125. And the n is m times t, so it's going to be 2 times 10, which will give us 20. Now, let's plug everything into the formula. Right, so you can plug it in straight in. So we got $11,538.34. So that's the answer. Now, how much interest did you earn? So how much money did you, after 10 years, it will be that this much money in the account, which is $11,538.34. So how much interest did you earn? Right, so we subtract the future value of what we just got minus what you invested, which is the present value. Right, which was 9,000. So it's going to give us $2,438.34. So that's how much interest you earned in those 10 years. Okay. Now this future value of an ordinary annuity, this is section 5.3. So here's the problem here. At the end of each quarter, a 50-year-old woman puts $1,200 in a retirement account that pays 7.2% compounded quarterly. When she reaches 60, what will be the value in the account and how much interest will she earn? So again, let's get the formula. This is the formula for the future value of an ordinary annuity. Again, there's 7 things. So let's extract the information. What are we looking for? Right, when she reaches 60, what will be the value in the account? So we're looking for the future value. The payments that she's making is $1,200, right? $1,200 4 times a year. The R will be 7.2%, 0.072. Here it says at the end of each quarter, right? Quarter means 4. So compounded anyway, here verifies it compounded quarterly. So M is equal to 4. The time, here's the time. Here's where a lot of students begin to make mistakes. Just because they see numbers there, they want to put them in here, which is not correct. So let's visualize it like a real life problem here. Say that you're 50. I mean, okay, say that I'm 50 because I'm older. Say that I'm 50, right? And I want to put this much money in the account every 3 months or 4 times a year. When I reach 60, what will be the value in the account, right? So if I wanted to do it when I'm 60, right, when I'm 50, so you're going to subtract 60 minus 50, which will give us 10. That's what the time will be. And again, I've seen a lot of students, just because they see numbers there and they have it in years, they want to put some of the values here because they don't know what actually is taking place with this problem here. So after you find your R, M, and T, you'll be able to solve for I and for N. So the I will be R divided by M, which will be 0.072 divided by 4, which will give us 0.018. And the N will be 4 times 10 because the M is 4 and the T and the time is 10, so it'll be 40. Again, let's plug into the formula. Let me show you how to use without clearing or stopping the calculator. This will help you with one steady flow. I was showing my students how to do this, and they took the exam today, and they did very, very good on the exam with these type of problems. Okay, so first you're going to enter the numerator here on your calculator, right? And this is what you see, right in black. Then without stopping the calculator, you're going to hit the division key, right? I mean, this is what you have here. Then you're going to hit the division key, right? Then after you see that, this is what you should see on your screen of the calculator. Then you're going to enter 0.018 and then enter it. Then this is what you should see, which means the 1.041320138 divided by 0.018 is going to give us 57.85. Right? Then what you do now, you hit the multiplication key because you're going to multiply this times the 1200. This is what you should see on your screen. And you can enter the 1200, and this is the final result. And round it off, right, to the nearest penny. It's going to give us something like $69,421.34. Some of my students from today, they mentioned that they use this PowerPoint because I loaded this PowerPoint, and they told me that this was how they were able to get some of the answers because this is how they would check their work by applying what I did here. So maybe you guys can use it also for your exam, right? So you can practice how to enter them without leaving the calculator. So how much money did you invest? So there was 40 payments, right? So you gave 40 payments, right? Let me see here. 40 payments at 1,200, right? So you multiply that 40 times 1,200, which will give us 48,000. So how much money did you earn? I mean, how much money did you invest, right? So really, it was 4,800 that you invested, because the 40 payments times the payment will give us 48,000. But this is how much money you got. So that means that you earned a lot of extra money, because this was the value in the account after the 10 years. But this is really how much you put in out of your pocket. So if you notice, you earned $21,421.34 in those 10 years, which is not bad at all. Okay. So this is the amount of money after 10 years, which is $69,421.34, and this is how much money you earned in interest, $21,421.34. Now I believe this is my last problem here. I believe it's already 4, but let me see if I can do it. Okay, this problem here, guys, is from section 5.4, and now we have a different formula. This is called the present value of an ordinary annuity. This is to purchase like an expensive item, and how will be the monthly payments. So number 20 states you want to purchase a house. I'll purchase a house for $225,000 with a 30-year fixed rate at 3.9%. What are your monthly payments, and how much interest did you end up paying? Okay, so again, we're looking for the payments, right? So the $325,000, we're looking for the payments, so that must be the present value, how much you're going to borrow from the bank right now. Okay, so then we know that R is 3.9%, which would be 0.039. Monthly means M is 12, and the time will be 30 years. So my I will be 0.039 divided by 12. Gives us something like 0.00325. And the N is M times T, which is 12 times 30. Give us 360. So plug everything to the formula. And this one here, guys, I'm going to show you how to do it in the calculator. Okay, so first, you're going to enter the numerator into the calculator, just the way it is. So once you enter it, this is what you should see on your screen, 0.689043691. Then, right, then you're going to hit the division key. Why? Because we're dividing this answer, right, by 0.0325. So after you press the division key, this is what you see on your screen, which means this answer divided by, then you're going to enter that 0.0325. Then you should see this in the screen, which means this right side, this whole in parentheses, this whole thing in parentheses is equal to 212.0134431. This is what you should see on the screen. Then I'm going to hit the inverse key. You press on the inverse key, and I believe I explained about the inverse key last week on the previous PowerPoint. So the inverse key will take this answer and invert it into the reciprocal, right? That's what it means. This answer is the inverse, and then I'm going to multiply that by the 325. By the 325,000 on the left side. So you're going to enter 325,000. Then you enter. So this is the answer here, guys. These are your monthly payments. Round it out to your nearest penny. It's going to give us $1,532.92. So that's your monthly payment. Okay, now. So I got the first part right? But how much interest did you pay? Eventually, when you purchase a house, right, they're going to charge you interest than the $325,000. See how much money you actually paid. So there were 360 payments, right? 360 payments. So I'm going to multiply the 360 times the payment amount. This will give you $551,851.20. So that's how much you paid for the house, okay, including the interest. So then, how much money did you pay extra for the house? Okay, so we subtract the total amount, right, minus the initial value of the house, which gave us $226,851.20. So you end up paying almost a quarter of a million, more of a quarter of $1 million more in interest. How can you avoid this interest? You can avoid this interest by actually paying more into the principal every month. Or if you cut, if you want the payment instead of 30, right? Instead, try to pay it in 15 years. You'll be surprised how much less interest you pay if it's in 15 years. When you buy a house for 30 years, right? The interest rate is going to be a little bit more. If you purchase it in 15 years, the interest rate will go down, but your monthly payments will go up. But eventually, you end up paying a lot less money than with a 30-year loan. Okay, that's extra help there if you're going to buy a house or something. So that's it for this PowerPoint, guys, and we went over like 5 minutes, but I'm real pleased that I got to finish it. Let me go back to the screen. Let's see here. Maciel, are you okay, Maciel? Did you have any questions?
Not at all.
Maciel, if you need help, come see me on Sunday. Okay, for doing studying numbers, because you're my student, right? So, or you can go to my office hours and get assistance. Okay?
Okay, I will. Thank you.
Thank you, my friend. Thank you.
Awesome. So thank you so much to Mr. Sassi for presenting some great material today to review for exam 3. I'd like to thank the audience for coming today and being a wonderful audience. We hope you have a wonderful spring break and good luck to everyone on their exams. If you do need assistance reviewing, there is online tutoring that can assist you with that. And then we're currently sharing the events that will happen after spring break, which will be March 25th. The first one's at 1 p.m. You're welcome to join that one if you have some free time, as well as joining the Happy Math Hour that occurs at 3 p.m. For 1324, we'll be covering systems of equations. With that, I wish everyone a happy spring break, and we hope to see you on the 25th.